Hi, thank you for your interest in the talk. I'm Sumegha, and this talk is based on joint work with Mark Braverman titled The Role of Randomness and Noise in Strategic Classification. The study of strategic classification was motivated by the following observation. Knowing information about the classifier, individuals might manipulate their attributes to get the favorable outcome. For example, if a student knows that a university heavily weighs SAT score in their admission process, she will be motivated to achieve a higher SAT score either through extensive test preparation or multiple tries. Such efforts by the students might not change their probability of being successful at the university but are enough to fool the admissions process. The question then is, how do we do meaningful machine learning amidst such manipulated data? We look into the setting of strategic classification, where the classification is part of the following game. Jury publishes a classifier first, then individuals, seeing this classifier, manipulates their features to get favorable outcomes, but while incurring certain costs. We assume that such manipulations don't change their inherent qualifications. What jury wants is to get a classification with respect to the true qualifications despite such manipulations. Let's start with the formalization introduced by Hart et al. In 2016 for strategic classification. X denotes the feature set, pi denotes the probability distribution over the features realized by the individuals, H denotes the true classifier. That is, Hx denotes whether an individual with starting feature X is qualified or not. Cx prime denotes the cost of manipulating from feature X to X prime. F is the classifier published by the jury. Knowing Cf, individual manipulates their features to delta X, and the final classification for an individual is based on delta X. The best response of the individual delta X is studied using Stackelberg equilibrium. In the equilibrium, the jury publishes its classifier first, and then the individual in response to F moves to the feature delta X. The individual manipulates its feature as long as the cost of manipulation is less than the advantage gained in classification. For example, here the individual tries to manipulate to a feature that is accepted by the jury as long as the cost is less than 1. The payoff to the jury is the probability that the final classification with respect to delta X is the same as the true classification with respect to H. We study a variant of this model with randomness. There's a lot of recent work in the field of strategic classification, and a lot of different aspects of the problem have been studied, as evident from some of the works mentioned below. The first set of papers focus on learning optimal classifier. For example, investigating the sample complexity of learning optimal classifier when the cost function is known, or even when the samples are themselves manipulated. Then there's another set of papers that study mechanism design under strategic manipulation. For example, to design mechanisms where individuals reveal their true data. Then the third set of papers study strategic classification when certain manipulations actually change the inherent qualifications. Then there's another line of work that discusses the fairness concerns associated with strategic classification. In addition to many fairness concerns associated with classification, strategic classification adds to this list. Different costs of manipulations across subpopulations can lead to disparate impact of strategic classification. For example, a high weightage of SAT scores for university admissions favors the subgroups of the society that have the resources to enroll in test preparation or attempt the test multiple times. There are papers that study this disparate impact on subpopulations. For example, Milley et al. Quantifies the disparate impact as social burden to a subpopulation. Hu et al. Studies the effect of interventions in strategic classification in the form of subsidies to disadvantaged group. In this work, we study addition of randomness and noise to the system. It is easy to see that randomness and noise doesn't improve jury's accuracy in the case of no strategic manipulation because we are losing information. But there are many examples in game theory where loss of information helps equilibrium outcomes. In fact, there are papers in fairness community that shows that hiding information serves fairness. And then there is a recent work by Frankel et al. That closely relates to our current work and shows how underutilizing manipulated data implies more information retrieval. In this work, we consider two modes of adding randomness to the system. First is by allowing the jury to publish a randomized classifier f, where fx is the probability of an individual with feature x being classified as 1. Second is to add noise to the features. Every individual has an associated private signal y, and the features x are noisy representations of this signal y. Pyx is the probability of seeing feature x when the y is the private signal. Jury bases their classification on the features. We show through examples that randomized classification and addition of noise to features can lead to better equilibrium outcomes, that is, better accuracy and fairness compared to deterministic classification. Then we also highlight the advantage of using the mode of adding noise to the features over randomized classification. Let's dive into the model of randomized statistic classification. First, we look at the formal setting. In purple are the changes in the setting that are made from Hart et al. Paper. X is a feature set which we consider to be one-dimensional. Pi is the probability distribution realized by the individuals over the features. H is the true qualification function, which we also consider to be probabilistic. That is, h of x denotes the probability of an individual with feature x being qualified. C is the cost function, and we assume that the cost function is simple, whose definition we will see in the subsequent slides. Most importantly, jury publishes a probabilistic classifier f. Knowing C and F, individual manipulates their features to delta x as seen on the next slide. Again, in the Stackelberg equilibrium, the jury publishes the f first, and then an individual looking at f manipulates its features to delta x, which is defined using the following method. An individual looks at the set of features such that the advantage gained in the probability of acceptance is greater than the cost of manipulation. Then it moves to a feature in the set with highest probability of being classified as 1. This is the best response of an individual. Next, we look at some measures of optimality for strategy classification. First is classification accuracy, which is jury's utility and is defined as follows. The final classification for a feature x is denoted by f of delta x, and the actual qualification for that feature x is h of x. Therefore, u of f just represents the probability that the jury classifies an individual correctly. Note that the jury ideally would want to come up with the f such that f of delta x is 1 for all h of x greater than half and 0 otherwise. The second measure of optimality that we consider is efficiency of a published classifier, which we defined as the utility of the classifier minus the expected effort put by a qualified individual at the Stackelberg equilibrium. That is, a classifier f is penalized for the extra effort put by qualified individuals. For example, to allow for strategic manipulation, jury raises the bar for acceptance, which results in extra effort put by individuals that would have been accepted otherwise when jury wasn't accounting for strategic manipulation. Various efforts put by an equally qualified individual in two subpopulations when the cost of manipulations are different is a fairness concern. A recent paper studied related quantity, which they called social burden for a subpopulation. Now that we are done with the definitions, let's look at a simple example which shows that randomized classification can strictly improve the accuracy and efficiency compared to deterministic classification at Stackelberg equilibrium. In this example, our feature set is just two features, A and B. Number of individuals having the features A and B are equal. The individuals at A are not qualified, whereas the individuals at B are qualified. The cost of moving from A to B is 0.6. As the cost of moving from A to B is less than 1, if B is classified as 1 and A is classified as 0, everyone at A will manipulate their features to B. Hence, any deterministic classifier cannot distinguish between the features A and B, and thus has accuracy and efficiency of at most 0.5. Next, for the same example, we give a randomized classifier that achieves accuracy and efficiency of 0.75 at the Stackelberg equilibrium, much better than any deterministic classifier. The classifier F accepts individuals with feature A with probability 0.5 and the individuals with feature B with probability 1. An individual at A doesn't have any incentive to manipulate to a feature B because the difference in the probabilities of acceptance, which is 0.5, is less than the cost of manipulation, which is 0.6. This classifier thus has accuracy and efficiency of 0.75 at the equilibrium. On a high level, jury selects unqualified individuals with some probability so as to de-incentivize them from manipulating their feature and hence achieving better accuracy and efficiency. In fact, we show that for simple cost functions defined on the next page, the optimal solution in terms of efficiency is where players never manipulate their features. That is, the randomized classifier is structured in a way such that the gain in the probability of being classified as 1 does not justify the expense of changing one's feature. A simple cost function has the following properties. First, all the costs are non-negative. Then, manipulating to a lesser qualified feature is free. That is, Cx, x prime is 0 whenever h of x prime is greater than or equal to h of x. Third, the costs are subadditive. That is, cost of changing from x to x double prime is lesser than the cost of first changing from x to x prime and then from x prime to x double prime. We prove that for simple cost functions, the most efficient randomized classifier is such that the best response of all individuals is to reveal their true features. That is, the best classifier in terms of efficiency, F, is structured in a way that it is Lipschitz with respect to the cost function C. That is, the difference in acceptance probabilities at x prime and x is less than the cost of manipulating the feature x to x prime. But we also observe some obstacles to using randomized classification. Firstly, it might be unacceptable to use probabilistic classifiers. Secondly, randomized classification leads to instability in the system. Why? Because once the individuals reveal their true features, then jury can conveniently change its classifier to the one that achieves best accuracy given the true features. This is particularly important for the more complicated scenario of multiple classifiers such as college admissions, where the effect of each jury on the overall market is very small. Hence, the jury doesn't have any incentive to stick to a randomized classifier for the benefit of the market as a whole. In fact, we prove formally that whenever a published randomized classifier achieves strictly higher accuracy compared to any deterministic classifier under Stackelberg equilibrium, jury has an opportunity to get strictly better accuracy by using a classifier different from the published post the Stackelberg equilibrium, hence creating instability in the system. Now we shift to the second mode of adding randomness to the system, that is noisy features. Here we exploit the power of randomness in strategic classification without the obstacles to randomized classification. Firstly, we formalize the setting of strategic classification with noisy features as follows. Every individual has an associated private signal y. Given y, the feature x is drawn from distribution py. For example, py can be a Gaussian distribution with mean y and variance 1. Next, pi y represents the population density with private signal y. H of y denotes the probability of an individual with signal y being qualified. The jury's classification is based on the feature x and it publishes a deterministic classifier for the Stackelberg equilibrium. An individual can manipulate its private signal to y prime, that is, it's pretending to have a higher private signal y prime, incurring certain cost which is equal to cy, y prime. We assume that the individuals can't control the noise. For example, one can manipulate their chances of getting a higher SAT score, but the final score is still noisy depending on other factors than preparation. Knowing C, F, and the noisy distributions, individual manipulates its signal to delta Y. I want to again emphasize that the classifier is deterministic. We first look at this quantity Q of Y, which is the probability that an individual with private signal Y is accepted by the jury. The randomness comes from the noise even though the classifier is deterministic. The best response of an individual with private signal Y is defined similarly as it was defined in the previous strategic classification settings. That is, a player moves as long as the advantage in acceptance probability justifies the cost. Note that the best response of an individual imitates that of a randomized classification even though the published classifier here is deterministic. Classification accuracy, which is jury's utility, is defined same as before. Here Q of delta Y is the acceptance probability for an individual with private signal Y, and H of Y is their qualification probability. Thus U of F just represents the probability of correct classification with respect to H. Next, we give a simple example which shows that the use of noisy features can give better accuracy than compared to when no noise is added to the features. Let's assume an individual with private signal A private is not qualified and the one with B private is qualified. The observed feature is equal to the signal with probability 0.75. Let's look at a classifier that accepts everyone with feature B and rejects everyone with feature A. Then an individual with private signal A private is accepted with probability 0.25 and an individual with private signal B private is accepted with probability 0.75. Thus, an individual with private signal A private has no incentive to manipulate because the difference in the acceptance probabilities is 0.5, which is less than the cost of manipulation, which is 0.6. It is easy to see that the final accuracy of this classifier at Stackelberg equilibrium is 0.75. But for deterministic classification, when jury sees the private signal, that is, the features are not noisy representations of the private signals but are private signals themselves, then as seen before, accuracy is at most 0.5 because there is no way to distinguish between the signals A private and B private. Now that we have seen how the use of noisy features can improve jury's utility in the strategic classification setting, we look into the measure of fairness studied in the paper and show how the use of noisy features can also improve the fairness measure of the published classifier. Given two subpopulations S1 and S2, let pi1, pi2, h1, h2, c1, c2 be the respective functions. That is, pi1 is the probability distribution over the private signals realized by the individuals of subpopulation S1, h1 is the qualification function, and c1 is the cost function for subpopulation S1. Similarly, the functions are defined for S2. Given a classifier F, U1F and U2F represent the classification accuracies of the classifier F on subpopulations S1 and S2 at the Stackelberg equilibrium. The measure of fairness that used is the difference between these classification accuracies. Note that the jury's utility is the classification accuracy over the entire population, that is, the subpopulation accuracies are weighted by their population density. Throughout the examples in this talk, we assume that there are only two subpopulations S1 and S2, and we assume that they have different cost functions C1 and C2 but have identical qualifications, that is, pi and h are the same for both of them. This is to emphasize the unfairness caused just because of strategic manipulation. We showed through examples that the use of noisy features can improve both accuracy and fairness measure of the published classifier compared to the setting when no noise is added to the private signal. Particularly, we gave example of identical qualifications and set of cost functions such that if the size of S1 is less than the size of S2, that is, S1 is a minority, then in the no noise setting, S1 is always at a disadvantage at the Stackelberg equilibrium. More formally, the classification accuracy for S1 is always less than the classification accuracy for S2 for utility maximizing function f under Stackelberg equilibrium in the no noise setting. Moreover, we give examples of cost functions C1 and C2 and noise distribution such that if we add this noise to the setting and consider the utility maximizing f prime under Stackelberg equilibrium for noisy features, then the classification accuracies of f prime for both the subpopulations is exactly equal. Moreover, the jury's utility at f prime is greater than the jury's utility at f. This is an example where noisy features can improve both accuracy and fairness simultaneously. To summarize, we saw that both randomized classification and noisy features can improve accuracy, efficiency, and fairness of a published classifier in the strategic setting. Now, something for the policy perspective. It is easier both practically and legally to commit to using noisier signals, for example by restricting the types of information available to the jury, than to commit to disregarding information ex post, which is required for successful randomized classification. Thank you.